By the time Halley's comet returns to the inner solar system, many of the people who first watched this video will be old enough to show it to their grandchildren, and it will look noticeably different from the last time humanity saw it. Its next appointment with Earth's skies is already booked in celestial stone, the year 2600. That date is not a guess, not a rough estimate. It comes from solving Newton's laws of motion and universal gravitation for a very specific problem. A roughly 11-kilometer-long, misshapen chunk of dusty ice, falling around the Sun on an elongated, tilted, and constantly evolving path. Halley's orbit takes about 75 to 76 years to complete, but the exact length of each lap changes slightly, because gravity is not a polite, isolated force. Every pass, the comet feels tiny tugs from planets, especially Jupiter and Saturn, and even smaller influences from outgassing jets. Streams of gas and dust erupting from its surface like microscopic thrusters. Add all that up with modern numerical simulations, and you get a very precise answer: perihelion. The moment Halley is closest to the Sun will occur in 2061, around mid-July, with predictions narrowing down to the level of days. But here's why 2061 is especially exciting: geometry. When Halley came by in 1986, Earth and the comet were arranged in a slightly disappointing way. From our point of view, Halley passed on the far side of the Sun, and we saw it after perihelion, when its activity had already begun to decline. That made the comet comparatively faint, at least compared to some historical showings. In 2061, the configuration is flipped. Earth will be on the same side of the Sun as Halley as it swings through perihelion. That means two very important things. First, the comet will be physically closer to us during its most active, most illuminated phase. Second, the sunlight will hit its dust tail in a way that is more favorable from our vantage point, like shining a flashlight through smoke, so that you see the beam, not just the light source. Combined, these factors should make Halley significantly brighter than in 1986, potentially bright enough to see with the naked eye even from moderately light-polluted locations, especially if you know where to look. So, what will you actually see, standing under the sky of 2061? If conditions cooperate, clear air, a dark side far from city lights, and the comet performing roughly as expected, Halley could reach an apparent magnitude of around 0 or even slightly brighter. In astronomical terms, magnitude is a logarithmic scale for brightness. Each step of one magnitude corresponds to a factor of about 2.5 in brightness. A zero-magnitude object is about as bright as the brightest stars in the sky, like Vega, and a comet at that brightness, spread out into a glowing coma and tail instead of a pinpoint, can look surprisingly impressive. You will not see a blazing science fiction streak spanning half the sky. That's artistic license. But you could see a distinct fuzzy head, the coma, perhaps as large as the moon's apparent size, with a tail stretching several degrees, maybe as long as 3 or 4 times the width of your outstretched thumb at arm's length. Through binoculars or a small backyard telescope, the view becomes richer. The central condensation of the nucleus, subtle structures in the inner tail, maybe even faint jets curving away as the rotating nucleus sprays out newly liberated gas and dust. Behind that view is a delicate interplay of physics and chemistry. As Halley falls inward toward the Sun, the solar flux, the power of sunlight per square meter, climbs dramatically. At Earth's distance, 1 astronomical unit, the Sun delivers about 1,360 watts per square meter. At Halley's perihelion, roughly 0.6 astronomical units, that becomes almost 3 times stronger. Ices embedded in the comet, primarily water ice, but also carbon monoxide, carbon dioxide, methane, and others, absorb this energy and start to sublimate. They turn directly from solid to gas without becoming liquid because the pressure in space is so low. This gas seeps through the porous crust, dragging out dust grains, and emerges through vents and fractures as collimated jets, essentially natural thrusters. The gas expands into a surrounding cloud. The coma, which can grow to tens or even hundreds of thousands of kilometers across, while the dust and gas are pushed away from the Sun by radiation pressure and the solar wind, creating the tails we see. One intriguing detail: what you see in the sky in 2061 will not be exactly what your great-grandparents saw in 1910, or what spacecraft saw in 1986. Each passage, Halley changes. We know this because we have direct before and after comparisons. When ESA's Giotto probe flew past Halley in 1986, it mapped a dark, potato-shaped nucleus about 15 by 8 kilometers in size, with only a few % of its surface actively venting material. Since then, Halley has spent decades in deep freeze at the outer reaches of its orbit, but every time it comes in, another fraction of its surface is eroded. Estimates suggest that on each perihelion passage, Halley might lose on the order of a few meters of its radius. That might not sound like much for an 11-kilometer object, but integrated over tens of thousands of years and hundreds of orbits, it matters. It means that the Halley of 2061 is slightly smaller. Its spin state may have changed due to uneven outgassing torques, and different vents may be active, altering the pattern of jets and, in turn, the structure of its tail. That evolution is not just cosmetic. It is central to why Halley still matters to astronomy today. Short-period comets, like Halley objects that return within a human lifetime, are laboratories for studying how primitive solar system material survives and changes over time. Many of the ices inside Halley formed in the cold outer regions of the protoplanetary disk over 4.5 billion years ago. They preserve a chemical and isotopic fingerprint of the early solar system, the ratios of deuterium to hydrogen in its water, the presence of complex organic molecules, the distribution of noble gases. Every time Halley returns, astronomers refine measurements of its spectrum, the pattern of light it emits and absorbs, and track how its activity profile changes. Are certain jets weaker? Are new volatiles exposed? Does the onset of activity begin further from the Sun or closer? These details feed into models of cometary aging, telling us how long comets can survive, whether they might contribute organics to planets, and how the population of comets evolves over millions of years. And Halley's influence extends well beyond the times it is visible as a comet. Even when Halley is far out in space, its ghost passes through our skies twice every year. When Halley travels through the inner solar system, it sheds dust, tiny grains ranging from micron-sized particles to millimeter-scale pebbles. These particles spread out along the comet's orbit, forming a meteoroid stream, like debris scattered along a highway. Earth's orbit intersects this stream at 2 points. When our planet plows through these clouds of Halley dust, the grains slam into our upper atmosphere at tens of kilometers per second, compressing and heating the air in front of them until it glows. To us, that glow is a meteor, a shooting star. The Orionid meteor shower in October and the Eta Aquarid shower in May are both caused by debris from Halley's comet. So even in years when the comet itself is a frozen, invisible ember trillions of kilometers from the Sun, its fingerprint is etched across our autumn and spring skies.